to talk about statistical analysis of PDL penalty on coherent transmission technologies based on WSS experimental characterization. I'm Andrea D'Amico, I'm from Politecnico di Torino, and I'm doing my PhD under the supervision of Professor Vittorio Curri. So in this work, the general framework is this open disaggregated optical network, where we have this hierarchy of the structure of the network controller. So where we start is this software-defined network controller, which has, in an open and disaggregated optical network, has access and can manage all the components and subdomains of the entire network. And so I divided here in this picture the transceiver, which generate and receive the signal. Then we have the ROADMs that can equalize and switch each channel. And then we would have the OLS controller that manage the optical lens system. And in an open and disaggregated network, we have access of all these points. And what we want in such a scenario is a metric which allows us to properly configure the transceivers as choosing this in the right symbol rate and modulation format. And also the same metric has to be used to optimize all the optical lens systems. And in particular, you have to fix the launch power and the amplifier working points. So one thing that usually is done in this scenario is to use the GSNR, the generalized signal-to-noise ratio, as a quality of transmission metrics. And this can be done assuming each light path has an additive and white Gaussian noise. And this means that the total metric, the total GSNR from source to destination, can actually be evaluated as the proper inverse sum of the GSNR of each subdomain crossed by the propagation. Once we have this metric, which is the generalized signal-to-noise ratio, we can evaluate, for example, the lightband deployment and modulation format feasibility, as we can invert the SNR versus BER functions, which change with the modulation format. And so the main point is that we have this spec threshold, and we know that the different values of GSNR allows different values of the modulation format that we can deploy, and this would be a different capacity that we can reach. Of course, the higher the GSNR, the higher the capacity that we will be able to deploy. So in reality, what you have, if you want to create a physical layer aware quality of transmission estimator, is not just this metric, the GSNR, which actually can be, as we said, it can be evaluated as the proper sum of each subdomain. So, for example, we would have the ROADMs that equalize the signal, the fiber that introduce loss and nonlinear interference noise, and the amplifiers that introduce the gain and the amplified spontaneous emission noise. And with these parameters, we can reconstruct the GSNR of the system. But we don't have only this metric that depends only on the physical layer, but we have also some penalties that comes from other effects in the propagation. For example, the PDL, which is the focus of this work, but also the dispersion, the PMD. And all this penalty has to be considered in the end, because this penalty would result in margin, system margin that you have to apply. So, as I said, today I'm going to focus on the PDL, and also I just consider the noise generated by the amplifiers. So in this work, actually, I'm not considering generalized signal-to-noise ratio, but only the optical signal-to-noise ratio, which usually is represented as the ratio between the signal and the amplified spontaneous emission noise. And what I want to focus here is the effect of the PDL on this signal-to-noise ratio, and and also give a perspective of a proper management of this degradation. So just to mention in general, what is done is so you can accumulate these GSNR metrics, and also you accumulate this this PDL, which is introduced by each device through the propagation. And what you want in the end is a penalty, which is a function of this total PDL. And usually the PDL in a common solution is, let's say, accumulated with this formula, which is just the sum of the squares of the PDL introduced by each device. And the main point of this work is to prove that this approach actually cannot work. And to understand this, we have to go deep in what happened with the system with PDL. And here is just let's say picture the effect of the PDL. So what we have is starting from this dual polarization signal, and then we have this kind of device, which are the ROADMs and the amplifiers, which introduce so a polarization dependent loss, which is the PDL. And this usually the axis of this maximum and minimum loss are not aligned with, of course, with the transceiver X and Y, which are actually arbitrary. And so you're gonna have a loss which depends on the polarization. Then usually what you simulate in this physical layer simulation is the polarization rotation induced by the fiber. And then you're gonna have other devices as the EDFA, which add this noise, which we consider here, which would be the amplified spontaneous emission, and then apply also a PDL. In the end, what I plotted here is the effect of the receiver. So you recover the polarization at the receiver, and the metrics that you have at the end are the GSNR or OSNR on the two separate polarization direction. And here you can see that so the point is that if you have only one single aggregated metric for the PDL, the only thing that you can do is propagate the signal with this PDL, which would create a distribution of the final signal power on the two polarizations, and then just divide the noise accumulated at the end. So you don't apply any PDL to the noise. And what you would obtain is a distribution of the OSNR, which is as large as the distribution of the signal. So this distribution here is a variation from the expected signal induced by the PDL, the total PDL given by the entire OLS and the ROADMs. And you can see that this would create this penalty here, which so as you have this OSNR variation on both polarization, what you are interested is the lowest value of OSNR that you have, because this would put the threshold of your performance, and so this will create this penalty with respect to the nominal value, let's say, of the OSNR. Another thing that you can do, of course, is divide first the noise. So in this case, you are simulating such a system where all the noise is at the input of the system, and then apply the PDL. But in this case, you won't see any effect of the PDL, because, of course, both these signals, the real signal and the noise, would be affected by the same PDL. So in the end, this effect cancel out. So the reality, so the most adequate way to simulate this is actually introducing the noise in different points along the line, and also the PDL given by each device, and take into account that the noise and the PDL are actually introduced in a distributed way along the entire optical lens system. And in the end, what you would obtain with this procedure is a distribution which is actually more steep around the nominal value of the OSNR, and so you can obtain a smaller penalty. And of course, this would be in the middle between the two extreme cases that I pictured before. So in order to have some realistic simulation of this effect of the PDL on the OSNR, what we have done is experimental characterization of a WSS. So in particular, we consider 1 times 16 LCOS WSS, and we measure the PDL induced on here you can see the experimental setup. So we had an ACL, a polarization scrambler that would, let's say, reproduce the polarization scrambling induced by the fiber span. And then we have the WSS, which will be characterized, and a power meter at the end. So what we measure is this PDL, so the difference between the maximum loss measured and the minimum loss measured. And we have done this varying 16 ports of the WSS, 9 frequency along the C-band, and 5 values of attenuation. And what we can observe here is that all the fixed the attenuation, all and varying the ports and frequency, we can observe a similar distribution whose average increase with the increasing of the attenuation. Is that you can see here that the variation, so the standard deviation, if you want, actually remains constant for all the attenuation. So what you have is kind of a translation of this distribution of PDL increasing the attenuation. So given these values of the WSS distribution of PDL, we have done this PDL transmission scenario where we want to show the effect of considering the PDL and the noise introduced in a distributed way along the entire optical lens system. So we divided the optical lens system in 2 domains. Let's say there is the regional domain, which is characterized by longer span. And so the main characteristic here is that this long span induce an eye loss. And so you're going to have an higher gain to recover all the loss through this propagation. And instead, you have just 2 ROADMs. So the number of ROADMs, which are the devices that introduce the most of the PDL, are less than a metro domain scenario, where actually you have shorter lines, shorter fiber span. So the amplifiers would recover less loss, but you have a higher number of ROADMs, so a higher value of PDL. So just to recap, to summarize, in the regional domain, we're going to have more gain, and in the metro domain, we're going to have more PDL. Here are the value that we use. So for the WSS, we select an attenuation average of 5 in the case of metro, because in here we're going to expect less ripple accumulated because we have less amplifiers. And in the region instead, we expect a higher attenuation for the equalization given by the ROADM. And the PDL in metro and regional both are extracted by the distribution that we experimentally measured. Instead, for the EDFAs, you can see that in the metro, where we have a lower gain, we have a higher noise figure, especially for the booster. And for all the cases, we selected this 0.2, which is characteristic for the amplifier. Here are the results that we obtained for the two transmission scenarios, so from the regional to the metro, and then vice versa from metro to regional. You can see that the final SNR distribution are pretty different. In orange, you can see the distribution of the OSNR as if all the noise is located at the end. So in this case, we are applying the PDL only to the signal, and this would be this aggregated PDL approach, which doesn't work in the case of, for example, here from regional to metro. Instead, the blue distribution is the simulated distribution, and you can see that is more steep than predicted from this aggregated approach. Vice versa, in the case where we go from metro to regional, you can see that the regional case, which has higher noise, is more similar to the case where we apply the noise all at the end. So to conclude, we had an experimental observation of this 1 times 16 LCOS WSS. They have a similar PDL distribution, and these distributions increase when we increase the attenuation. And from the simulation observation, we had this. We proved that this single accumulated PDL metric cannot be applied. And if we apply such an approach, we're going to have a wider statistical distribution and so wider margins with respect to the reality. And more importantly, this PDL and noise management won't be distributed along the line. So this would provide inaccurate accumulation and an inaccurate prediction of the PDL induced OSNR variation. So thank you.
Okay. Due to time limitation, I think we have to directly move to the next presentation. I think the next presentation from the same group. Am I right?
Sorry, I have some difficulties to hear you.
Could you hear me? Yeah.
Yes. Now, yes.
Yeah. I think we have to directly move to the next presentation. I think from the same group.
Okay, so I'll go.
Observation of the disaggregated linear interference noise generation.
So I'll go with the next presentation.
Yeah, please.
Yeah, okay.